Good morning, chemistry friends. Hopefully you had a nice but somewhat soggy weekend. And hopefully Friday went well for a lot. Some of you, I know you've turned in stuff and just getting stuff cleaned up so we can be current. And again, all this week, when you have a little bit of work time, like there's really nothing today other than passing along some information. Again, don't look at the big pile of late stuff I may have to get done in the last few weeks that we have here. Just pick one. Just pick one, work on it, stop into office hours, ask questions, email, whatever it is. Let's just get it done. Let's just get it done so we can just get through the last of this term, socially distanced and distance learning and move on. Anyhow, last Thursday, when we last had some new learning, we just started our acid base unit, and it was really just going through definitions of different types of acids, how to account for things that have hydrogens, don't have hydrogens, have hydroxides, don't. 99% of our work is going to be right here with the Arrhenius definition, just like when we talked about naming a couple terms ago and learned how to name acids and bases. We say that acids start with a hydrogen, bases end with hydroxide. Or when I dissolve them in water, the acid increases the amount of hydrogen ions in that solution. The base increases the amount of hydroxide ion in solution. What we're going to look at today is something that you've learned in science before about pH, but really the math of where it came from. And then all we're doing is introducing it today. Then tomorrow, we will walk through some problems on how to use it, and then give you some time to work on some problems in practice. All right, so let's skip ahead to where we need to be, which is here. In order to understand pH, you have to understand water. And you have to understand that water, like acids, like bases, will, in a sense, dissociate or dissolve itself. That there is always a certain amount of hydrogen molecules that will share hydrogen. Basically, like we showed up here before, we showed, if you go back and look at acid stuff before, we showed mixing, say, hydrochloric acid with water, and you get the hydronium ion and, say, the chlorine ion. Well, water with water, one of these hydrogens can hop to the other one, and that's called self-ionization. And you get that hydronium ion and that hydroxide, and it shows it here. And this is an equilibrium thing that just is going on rather rapidly, actually, back and forth. But the shorthand is this. Water is considered to be amphoteric. It is considered, as we mentioned before, it can be both an acid, because it kicks out a hydrogen ion when it dissociates, and it can also be a base. It kicks out hydroxide ion when it dissociates. And so when they talk about an acid and a base and pH levels, and the Arrhenius definition of an acid increases hydrogen ion or a base increases hydroxide, this is what we're talking about. When I'm putting it in water, there's already a small amount of hydrogen and hydroxide there anyhow. So even in just pure water, you've got all these water molecules. They're always kind of going apart, coming together, going apart, coming together, right? So they're kind of, one is always kind of throwing a hydrogen towards the other, and you're doing this constantly. Now it's an equilibrium, so the concentrations don't change. It's just the fact that the reason water conducts electricity is because it does separate into its ions. And then and it's also one of the things, as we learned a long time ago, that helps make things dissolve in it, ionic compounds and polar compounds and whatever. But for acid-base stuff, it's because then when I mix something with it, one of these is going to change. Anyhow, getting well ahead of ourselves. This is called the self-ionization of water. It happens at a set rate. At any given time, there's a very small amount of water molecules that are dissociated into hydrogen and hydroxide. It's constantly, every molecule is constantly going in and out of this phase, but only a small number at a given time, picture of time. And again, it's just saying that water is the basis for judging pH, is the best way to say it, because of the changes here. Self-ionization, don't worry about naked protons and ionic dipole. all that is talking about is how this is attracted to giving a hydrogen to here and stuff along that line. Okay. This is the big key idea. Okay. So here we go. Now, as we learn with equilibrium and reaction rates, then I can write up that equilibrium expression of the products over the reactant. So, and this is called an equilibrium constant or a dissociation constant, but the whole idea is at a given amount of time when it's in equilibrium, I can measure that concentration of hydrogen ions. I can measure the concentration of hydroxide ions, and I can know the concentration of water, and I can set up an equilibrium expression. Okay. Now, water is pure liquid. The concentration is constant no matter where you find the water in the world, because it's slightly changing now with pollution. But so you really don't need the water in the expression because it's the same everywhere. So really what your equilibrium comes down to is the concentration of the hydrogen and hydroxide. And so instead of calling it equilibrium, we just give it a W and say that's the equilibrium of water. Water's equilibrium number, okay, that will tell you, do I have more water or do I have more hydrogen hydroxide, is just by measuring the concentrations of the hydrogen hydroxide when it's at equilibrium. Now that number happens to be 1 times 10 to the minus 14th, which is why I told you that there is far more water than there is the ions in it. Because that's at any given, any given time, that equilibrium expression is 1 times 10 to the minus 14th. If you think of our equilibrium from the last unit, that means that there's very little ions, a whole lot of just undissociated water, just water molecules, but just small enough to conduct electricity and do all the things that water does to be the molecule of life. Now, since these are equal, and that's our equilibrium expression, it means that in pure water at any time, I have 1 times 10 to the minus 7th molar. So that's my concentration of hydrogen ions, is always 1.10 to the minus 7th in pure water. Nothing dissolved in it. Also the same for my hydroxide ion concentration. That's the start. And what I'm pointing out to you is 10 to the minus 7th, that's 7, if you remember your pH scale, is a key component to pH. All right. So the hydrogen hydroxide concentration in water is 1 times 10 to the minus 7th. And they call that the water equilibrium, to indicate what is that number at equilibrium when water dissociates and self-ionizes. Okay. We're also going to take that equilibrium into acids and bases. So this is just showing you that if you see the K, that just means equilibrium. If we're looking at A, then A means acid and B means base. So as we start looking at some of these numbers, and this is a couple days away, but these Ka and Kb start telling you how strong or weak an acid is. pH is not a great indicator of strong or weak. It can be, but it really is just an amine acid or a base. It's the equilibrium that tells you whether it's a strong acid or a strong base. So that's setting us up for that, but that's coming up. Anyhow, back to pH stuff. Because of that small number of hydrogen ion concentrations, remember water starting at 1 times 10 to the minus 7. The pH scale is a log scale. And if you remember from algebra, your logs, the reason people take logs of numbers is to take either very small or very large exponential numbers and reduce and kind of shrink them into a value you can use. Okay. So the formula for pH is taking the negative log of the hydrogen ion concentration. And why do we use a negative sign? Make sure that even the smallest concentrations of acids are positive value. Right? Okay. Anyhow. So if for just pure water, the hydrogen ion concentration is always 1 times 10 to the minus 7, and I plug it in the formula here and take the negative log of 1 times 10 to the minus 7, that's 7. That's the neutral pH. That's where that 7 number comes from in pH. It is from the equilibrium constant, the dissociation concentration of hydrogen ions in pure water all the time, everywhere in the world, no matter what. Okay. The higher this number goes, right? So as I say, dump an acid into water and dissolve it. The higher that hydrogen ion concentration goes, you know, from maybe 1 times 10 to the minus 6 or 1 times 10 to the minus 5th or something along that line, then the lower that number is going to go, right? So that number is going to get lower than 7. Correct? Oops, went one too far. All right, so 7 is neutral. That's where we started. I put something, I dissolve something in the water. If that number goes below 7, then it means I raised my hydrogen ion concentrations and I'm now acidic. If I throw in something basic, then really it's lowering the hydrogen ion concentration because it's raising hydroxide. If hydroxide goes up, then hydrogen has to go down because, again, going backwards, they're a balancing act. They're always in equilibrium. So it will shift the equilibrium to balance them out. So if this goes up, hydrogen ions go up, hydroxide goes down. If hydroxide goes up, hydrogen goes down. So going back to my formula then, stuff that is basic is throwing more hydrogen ions in concentration, which means, or hydroxide in the solution. So the hydrogen ion concentration will go down. Okay. So that's why as the hydrogen ion concentration goes down, that number gets bigger. And that's why we indicate anything over 7 as basic or alkaline. And here is just a chart of different things. Stomach acid, real strong. Actually, not 0, 0, but it's close. pH is not quite 0, but anyhow. For regular hydrochloric, here's hydrochloric acid in your stomach, lemon juice, citric acid type stuff, orange juice, whatever. And then baking soda, ammonia solutions, and everything else. Blood is slightly alkaline. Now, you may or may not know that there is also a pOH scale, which is really just the same thing, but you're measuring hydroxide. Now, the pH scale is more popular, the one you know, the one they talk about, the one that is commonly used and mentioned. But pOH is just the same thing, as you can see by the formula, just measuring hydroxide ion concentration instead. And so if somebody asks you the pOH, it's actually flip-flopped. Okay. In pOH, the lower numbers are the bases and the higher numbers are the acids. So it's really just the opposing function of pH because it's measuring the other thing. And again, it comes to the same deal. You start at 1 times 10 to the minus 7th in pure water. That means that the pOH neutral is 7. Okay. As hydroxide ion concentration would go up, the number would get lower. So bases are on the lower end of the pOH scale as opposed to the higher end in pH. If I was to throw in an acid and start increasing hydrogen ions and lowering the pOH as the OH number goes down, then the numbers get higher and the pOH, so the acid side of the pOH scale is the high numbers. It's not a big deal. We're not going to work on that a whole lot, but here the big idea is this. Hydrogen and hydroxide are always in equilibrium. Okay. And we know that overall, if I took the negative log of the equilibrium constant 1 times 10 to the minus 14th for the whole dissociation reaction, I get the number 14. And since H and OH added up, or H and OH multiplied together, are 1 times 10 to the minus 14th, then with the log, if I just add them up, they're equal. So they'll equal 14. So if the pH is 3, the pOH has to be 11. If the pOH is 2, then the pH has to be 12. Okay. So that's another way that we can measure stuff is knowing that since hydrogen and hydroxide concentrations are always equal in water, pure water, both at 1 times 10 to the minus 7, and I multiply those together, that gives me my equilibrium of 1 times 10 to the minus 14. If I take the log of everything through that, that just means that pH plus pOH will always equal 14. Okay. Now, here's where we're going tomorrow. This is the work we're going to do. From that self-ionization of water equilibrium expression, this was our equilibrium expression. This is what we figured out today, that these two multiplied together is always 1 times 10 to the minus 14. That means that these are always 1 times 10 to the minus 7th molar in pure water. Then we can find the pH as the negative log of the hydrogen ion concentration. If we needed to, we could find the pOH, so negative log of the hydroxide ion concentration. We know that the two added together always equals 14. And what we're going to see tomorrow is that if I know these concentrations, then I can figure out the pH or the pOH. Anyhow, this is what we're working with tomorrow. We are going to use these formulas to do pH stuff. That's our practice problems for tomorrow. This was just a setup of how all that pH stuff and all the numbers we can use comes off of this equilibrium expression for water right at the top. All right. Anyhow, there we go. That'll do it for today. Have a good Monday. Start a good kickoff to the week. We'll talk to you soon.